Oyster mushrooms are scientifically classified under the genus Pleurotus, belonging to the family Pleuritaceae. These organisms are saprophytic fungi, meaning they do not photosynthesize like plants. Instead, they obtain energy by decomposing lignin and cellulose present in dead plant material. The mushroom that we harvest is only the fruiting body. The actual organism exists as an extensive underground network of microscopic threads called mycelium. This mycelium colonizes the substrate, digests organic matter, and determines the yield potential of the crop. Successful cultivation therefore begins with supporting mycelial growth rather than forcing mushroom formation. The biological behavior of Pleurotus species makes them exceptionally suitable for protected cultivation. They thrive in high humidity, moderate temperatures, and low light conditions, all of which can be regulated inside a polyhouse. Because oyster mushrooms are not dependent on soil fertility, rainfall, or daylight hours, growers can control production through environmental management rather than seasonal timing. This alignment between fungal biology and environmental control is the foundation of year-round oyster mushroom cultivation. Oyster mushrooms can be cultivated in both low-cost sheds and polyhouse systems, but the outcomes differ significantly in terms of control, consistency, and scalability. In traditional shed cultivation, environmental conditions such as humidity, temperature, and airflow depend largely on external weather. While this approach has lower initial cost, it exposes the crop to seasonal fluctuations, inconsistent yields, and higher contamination risk due to dust, insects, and uncontrolled air movement. In contrast, polyhouse cultivation creates a semi-controlled environment. Humidity retention, moderated temperature, filtered ventilation, and diffused light allow growers to control biological timing instead of reacting to climate. This results in more uniform colonization, predictable fruiting cycles, improved hygiene, and the ability to plan staggered production batches. At commercial scale, this shift from reactive to controlled cultivation is what enables year-round production and stable cash flow. Commercial polyhouse mushroom units are typically divided into functional zones. These include a substrate preparation area, spawn incubation zone, and fruiting area. Each zone serves a specific biological purpose and requires different environmental conditions. This preparation improves hygiene, reduces cross-contamination, and allows batch-wise production planning. By managing each stage independently, growers can stabilize output and reduce operational risk. Oyster mushroom cultivation progresses through two distinct physiological phases: spawn run and fruiting. During spawn run, the mycelium colonizes the substrate and builds biological capacity. Fruiting occurs only after this foundation is complete. Many cultivation failures occur when growers attempt to induce fruiting prematurely. Yield potential is determined during the spawn run, not during harvest. Polyhouse systems allow this biological process to complete without stress. The spawn run phase typically lasts around 20 days. During this period, temperatures are maintained around 24 degrees Celsius, humidity remains moderate, carbon dioxide levels stay high, and complete darkness is required. Fungal metabolism generates heat internally. Poor ventilation or excess moisture during this phase can lead to self-heating inside the bags, killing the spawn. Careful environmental balance during spawn run directly influences final yield. Once colonization is complete, a controlled environmental shift triggers fruiting. Temperatures are reduced, humidity is increased, fresh air exchange is intensified, and diffused light is introduced. Carbon dioxide management becomes critical at this stage. High CO2 levels cause elongated stems and undersized caps, reducing market value. Fruiting is therefore both a biological and quality-driven process. Oyster mushrooms grow on lignocellulosic agricultural residues, such as wheat straw, paddy straw, sugarcane bagasse, and maize stalks. Substrate quality determines nutrient availability, moisture retention, and aeration. Proper chopping, soaking, pasteurization, and drainage eliminate competing organisms while preserving substrate structure. Poor substrate preparation is one of the most common causes of contamination and yield loss. Spawn is the planting material of mushroom cultivation and directly affects colonization speed, yield uniformity, and disease resistance. High-quality spawn produces fast, even mycelial growth and strong fruiting response. Inferior spawn increases contamination risk and delays production cycles. In commercial systems, spawn quality should never be compromised to reduce input cost. Bag preparation determines operational success. The substrate must be compact enough for mycelial bridging while remaining porous for gas exchange. Layer spawning distributes mycelium evenly, while peripheral spawning ensures oxygen availability near the plastic surface. Micro-perforations allow carbon dioxide to escape without drying the substrate. Consistency in bag filling becomes critical when managing thousands of units. Commercial viability depends on utilizing the vertical volume of the polyhouse. Hanging systems allow multiple bags to be suspended on each drop line, dramatically increasing production density. This layout improves airflow, enables uniform fogging, and ensures even fruiting across all bags. Vertical systems convert limited floor space into three-dimensional production zones. Each oyster mushroom bag produces multiple flushes, with yield declining gradually over time. By introducing new batches at regular intervals, growers can maintain continuous production. Rather than treating mushroom farming as a single harvest event, successful polyhouse operations function as rolling biological pipelines. This stabilizes labor use and daily output. Yield depends on substrate quality, spawn vigor, hygiene discipline, and environmental consistency. Most yield is concentrated in early flushes. Commercial systems prioritize predictable output across large volumes rather than maximizing yield from individual bags. Biological efficiency above 80% is achievable under disciplined management. Mushroom enterprises involve significant upfront investment in polyhouse structures, hanging systems, and climate control. Operating costs include substrate, spawn, labor, power, and packaging. Unlike seasonal crops, mushrooms generate income in short cycles, improving cash flow velocity. Profitability depends more on process discipline and batch planning than on peak yields. Most losses in mushroom cultivation result from microbial contamination rather than field pests. Green mold, bacterial rot, and flies thrive under excess moisture and poor hygiene. Preventive management through sanitation, airflow control, moisture discipline, and rapid removal of infected bags is far more effective than corrective treatment. At Seechur Agro, oyster mushroom cultivation is approached as a biological production system, not a short-term crop. Our focus is on aligning fungal biology with polyhouse engineering, environmental discipline, and batch-based production planning. Through research-backed articles and structured podcasts, Seechur Agro helps growers understand not just how to grow mushrooms, but why each step matters, enabling predictable yields, year-round production, and scalable protected cultivation models.